Example 8. A pair of dice is rolled 3 times. What is the probability that the sum of 7 will occur at least once? Write your answer as a percentage. So note that it does want the answer as a percentage. I'm going to go to the answer blank right now, and I'm going to put a percent just to remind myself that it has to be a percentage. I'm going to look at this, and it says the number of times is 3 times, so that means n equals 3 in this formula. And I know I'm doing that because I have that at least once. So the probability of at least once getting a 7 is going to be equal to 1 minus the probability of not getting a 7 raised to the number of times that we do the event. We're doing this 3 times, so we're going to raise it to the third power. Okay, let's think about this. What's the probability of getting a 7? We'll go ahead and look at that chart that we generated earlier with all 36 possibilities, and it seems to me that the probability of getting a 7 is 6 of the 36. I'm going to go ahead and simplify that to be 1/6. So the probability of getting a 7 is 1/6. So what's the probability of not getting a 7 then? Well, it's all the rest of them. So if 1 out of 6 times you get a 7, 5 out of 6 times you do not get a 7. Why do I care about that? Because that number right there, that probability of not getting 7, is what we're going to be using in our formula. So find the probability of getting at least 1 7 in 3 rolls. We're going to do 1 minus the probability of not getting a 7, which was 5/6, raised to the third power. When we do that, let's see what we get. I'm getting 0.42, rounded to the nearest hundredth, and as a percentage then, that would be approximately 42%. So what's the probability of getting 7 at least once in 3 rolls? You have a 42% probability. Let's try another one. It says, suppose a manufacturing process for a tableware produces 40 dinner plates, of which 3 are defective. If 5 plates are randomly selected from the 40, what is the probability that at least 1 is defective? Okay, so I see at least once. It says write your answer as a percentage, so I know I have to have a percentage. I'll put that down there now. At least once, so I want at least 1 defective. The probability of at least 1 defective, well, that has to be equal to 1 minus the probability that none are defective. Now this one's a little bit different because we can't just say use the probabilities as we did in the previous time. What we need to think about is how many ways can I pick 5 plates of 40. So now we're going back to what we did at the beginning of the semester, the chapter, which was about combinations and permutations. So here we're going to be using combinations because order does not matter. We're either picking the defective plate or not. Okay, so here's what we're going to think of. I want you to think of how many defective plates do we want, how many not defective plates do we want, and then how many total do we have. Okay, this is going to give us the probability of not being defective. So let's think about how many defective plates are there. Well, there's 3 defective plates, and of those we want to pick 0 of them. Again, I'm using combinations because order does not matter. I either pick the plate or I don't. How many are not defective? Well, there's 37 plates. All the rest of the 40 are not defective, so that's 37. And of those plates, I want to pick 5 of them. How many total plates are there? Well, there's 40 plates, and of the 40 plates, I'm going to be picking 5 of them. So I need to do 3 choose 0 times 37 choose 5 all over 40 choose 5. One thing I want you to notice is when you do this, that first number, when you add those first numbers together, you have to get the total of the first number in the denominator. And when you add the second numbers together, you have to get the total of the second number in the denominator. Make sure you're using the same sets. So this is saying we want 0 defectives. We want 5 not defectives over the total. This is going to give us the probability of picking no defective plates out of 5. So when I do this in my calculator and I round it to, I'll just go to 2 decimal places because it's going to want it the answer as a percentage. I'm getting approximate 0.66. I think it's 0.662, but we'll round down, so it's 0.66. So this is the probability that none are defective. The probability that none of the 5 are defective. Using the combinations formula, okay? So if I want to find the probability that at least one is defective, I'm going to do 1 minus that number. So that'd be 1 minus the 0.66, and this is giving me a total of 0.34, which is our answer of 34%. Again, we couldn't use this one like we did the last time because here we were doing multiple things at the same time. We were picking 5 plates at once. It wasn't like we were picking 1 plate and then 1 plate and then 1 plate. So we can't use the other method on this problem. We have to use combination formula. Let's go on to example 10. It says the winner of a contest will be blindfolded and then allowed to reach into a hat containing 31 $1 bills and 4 $100 bills. Notice that's a total of 35 bills in the hat. So the winner can remove 4 bills from the hat and keep the money. Find the probability that the winner will pull out at least one $100 bill. Find the probability that they'll pull out at least one $100 bill. So we know to find out the probability of at least one $100 bill, we're going to do 1 minus the probability of them being no $100 bills. So since we're removing all 4 of these at once, let's think about what we have here. Let's think about not hundreds, and then how many hundreds we have, and then the total. Okay? So of the hundreds, it says that there's 4 $100 bills. So of the 4 $100 bills, again, order doesn't matter. We just pick the money. So I want to pick 0 of the $100 bills times how many of them are not 100? Well, there were 31 that were not $100 bills. Of those, I want to pick all 4 of them. And the total of them, there was a total of 35 bills, and we're picking 4 of them. So this is going to give me my probability that none of them are $100 bills. When I put that in my calculator and I round, I'm ending up with 0.6 is what I'm getting on that one. 0.6. So I did 4 choose 0. There's 4 $100 bills. I want none of them. I did 31 choose 4. There's 31 $1 bills, and I want 4 of them. And then I divide that by the total, which is 35, and we're picking 4 different things. Again, combination or order did not matter. So when I do 1 minus the probability of no $100 bills, that would be 1 minus 0.6, which would give me a total of 0.4. As a percentage, that is 40% chance. So what's the probability that at least one $100 bill would be pulled? The answer is 40%. Notice, the total number of possibilities here, 35 choose 4, is a very, very large number. So on this problem, you would have to use this formula. It would be nearly impossible for you to list out all the different possible combinations and then calculate what percentage is that of the total. All right, so let's look at this next one. What's the Monty Hall problem? The Monty Hall problem is not on the test, but it's very, very interesting, and I want you guys to understand this. It happens all the time, or it used to happen on a game show all the time. And in this game show, there'd be 3 doors. It would be door 1, door 2, door 3. And that they would tell you that 2 of the doors have horrible prizes, nothing essentially. They were silly prizes like a goat or a pig or something along those lines. And 1 of the doors had a really good prize. So what they did is they let you pick a door. So I'll pick a random door. Here's the door X right here. So the question is, I'm picking door 2. What is the probability that it is the good door? Well, the probability that this is the good door, I'm locking it in right now, the probability that it's good would be 1/3. It's 1 of the 3 doors, and I know 1 of the 3 doors is good. So then what happens? The host says, okay, you have door 2. So the host looks at you and says, I'm going to open 1 of the other doors and show you something that's not the prize. So let's say they open door 1 and they say door 1 is a bad door, this one had the goat in it. Okay? So then they ask you, which one of the doors would you choose? Do you want to choose door 2, or do you want to stick with the door you picked, door 2, or do you want to switch over to door 3? And here's where people don't understand the logic. At this point in time, when I picked door 2, I locked it in. It was 1 of 3 doors. It was 1 of 3 doors, so its probability of being good was 1/3. But now, and that's locked in. We cannot change its probability. That's when I picked it. So now what we do is we look at what's the probability of door 3. Door 3, since door 1 has been exposed and I did not pick door 3, its probability is still open. its probability of being the good prize is now 1/2. So if they offered you, would you stick with the same door, you would have a chance of 1/3. If they said, if you switch, would you want to switch? If you switch, your probability would be 1/2. So the best thing you could do was to switch. This happens in many different game shows. I remember one, Deal or No Deal, where they had something like 30 cases of money. And you would sit there and they'd go through the cases of money and they would cross off and open some of the bad ones and they'd say, do you want to keep on going or do you want to? Okay, so at the end of it, you hopefully had one that had $1 million in it and one that had something low, I don't know, maybe $100 of it. And you picked your original case and it had a 1 of 30 chance of being that $1 million. Okay? When they ask you, do you want to keep that same case or do you want to switch at the end? When you locked in your choice, that was 1 of 30 cases. But that last case is a 1 of 2 probability of being that $1 million. So always what you should do in terms of probability is switch. Because as you switch, you're picking up a new case that has a much, much higher or much more favorable probability. It's weird to think, but the second you pick that case, the second you pick that door, you have locked in its probability, where all the rest of the cases, all the rest of the doors, their probability is continuously changing until you pick it and lock it in.